Good morning, everyone. Welcome to the next in our Asteroid Grand Challenge lecture series, which is sponsored by the Grand Challenge program at NASA headquarters and operated here at CERVI, NASA's Virtual Institute for Exploration Science. I'm David Morrison. I work at CERVI here at Ames Research Center, and I will introduce the speaker and also moderate the questions in the end. Questions, as I think you all know, can be submitted at any time on the web page during the talk or immediately thereafter, and then we'll see what we can get going on a dialogue with Tim. It's my great pleasure to introduce today's speaker, Tim Spahr. He has been interested in comets and asteroids since he was a kid, saw Comet Halley. He has attended the University of Arizona, degree in physics and astronomy, and he has been involved in the actual search for asteroids at the Catalina Observatory, which is the most productive today of our asteroid survey groups, primarily interested in software. But then he took a PhD in celestial dynamics, which does not, celestial mechanics, which does not mean that he has a wrench and works on celestial things, but in the study of the motions of objects, particularly in this case of near-Earth asteroids. He is now the director of the Minor Planet Center at the Harvard-Smithsonian Center for Astrophysics, and that is the central node for the whole world for taking in observations from both professionals and amateurs, massaging them, calculating orbits, telling the press what is or isn't going to come close. So he is certainly going to give us a fascinating talk today on the dynamics of near-Earth asteroids. Tim?
Thanks, David, for that introduction. It was very nice, and I'd like to say I've known you for, it's been about 20 years since we've been working together on this, and it's nice to see you. It's nice to be part of this program. Today, I'm gunning for talking for about a half an hour on the work of the Minor Planet Center, and I will also talk about how this fits in with the International Asteroid Warning Network. The work of the Minor Planet Center is quite varied and complicated, but it's the first bit, we're the first line of defense just for warning about anything that's going on. And we have many, many other things we do. Near-Earth asteroids is just one corner of it, but it takes most of our time. So I've got an outline here. I will try to go through this and be true to the outline. We'll see how I do. I'm going to talk about the Minor Planet Center's charter and responsibilities. And then I have to admit, I've always wanted to do this. I'm going to do a quick and dirty observation processing tutorial, including 3 extraordinarily complicated flowcharts. And I will try to work my way through those. If they don't come off so well, you can ask lots of questions. I'm gunning for having plenty of time to answer questions about how we do things. I'm going to discuss the handling of possible short-term impacts because that's really an important function of the Minor Planet Center. Now you'll notice I've got down this far and I haven't mentioned the International Asteroid Warning Network. The MPC fits in there, and after I've explained what we do, I will talk about the International Asteroid Warning Network. And I'm also going to talk about the future of asteroid surveys and near-Earth object surveys because there's a lot going on, and this field evolves, and it evolves in ways that most of us aren't really ready for all the time. So I'm sure something different than I will discuss will happen in the next year or two, and we'll adjust to it. So I'll talk about the MPC's roles and responsibilities. We are the world's nerve center for minor planet and comet observations. What this means is that all positional measurements of asteroids and comets that are made worldwide or in space are sent to this office, processed by our computers. It's our job to quality check these and distribute and publish them as fast as we can so that the community may get access to it. It's a completely international operation. As you see, we work with people in dozens of countries. We really must serve the entire community, and it's quite a challenge to do so. We also will take in orbits from certain people and publish those. It's also our job to provide discovery information for all the minor planets and comets, and even some satellites of the outer planets. One key job we have is alerting the world of impending impacts. And I'll talk about a couple of impacts that happened in the past for small objects, but it just goes to show we have a system in place. I've included an image of the Minor Planet Center building, but I would not want anyone to think that we get all of those offices. In fact, I'll put over here, I get one office sort of down in this area. There are only 6 full-time employees here, 6 full-time equivalents at the Minor Planet Center. So it'd be great to have a building that size, but there aren't that many of us working in the Minor Planet Center. Another thing that we do is help coordinate worldwide observers. There's quite a bit of follow-up needed for near-Earth objects and comets, and we try to assist with that in any way we can. It's a tough job. So in this slide, I'll talk about the many hats of the Minor Planet Center. We have a fairly complicated operation in terms of who we are answering to. I am operating this from the Harvard-Smithsonian Center for Astrophysics. The Minor Planet Center folks are all Smithsonian Astrophysical Observatory employees. We are not federal employees, however. We are a strange class called Trust Fund Indefinite, but we are not federal employees, and it's kind of important. If you think back to the issue we had in the fall with the government shutdown, we had this strange case of the Minor Planet Center working because we're not federal employees, and our bosses at NASA headquarters, Lindley Johnson, being furloughed. Very, very strange place to be, but there are benefits to not being federal. We are granted authority for operation by the International Astronomical Union, and we have been fully funded by NASA grants since 2008. So the way I like to think of that is that at any one point, it is my job to answer to 3 large and important organizations, that being Harvard-Smithsonian for Astrophysics, NASA, or the International Astronomical Union. It can present a challenge trying to make sure that all 3 groups are happy with the work that we're doing all the time. But I have to say I like it. I like being in that position. So what I'm going to go through here is the tutorial, how observations are processed. And I have to say again, this was a real kick for me because I got to go back to my old observing days and look at my old emails that I used to send to the Minor Planet Center. And as you can see, I was either sleep deprived or I had a silly sense of humor. But this is an email I sent to the Minor Planet Center announcing the discovery of a new near-Earth asteroid. This is the standard way that people communicate observations with the Minor Planet Center. We have a set format. As you can see, we've got some sort of keyword type things in here. This is your observatory code, which tells us where you are on the planet, what type of telescope you have, what star catalog you used, who the measurer was, who the observer was, and any other sort of information there. In this set down here, I won't explain every bit of it, but it has the time of observation, the right ascension, declination, and the magnitude. Those are essential things for computing any sort of starting orbit or any orbit. And it also tells you how bright the object is, so in case you want to go look for it, you know what you're looking for. So now I'm going to go into the ridiculous, complicated flowcharts. Hopefully you'll have some questions about this in the end. I'm going to call up my little pointer and I'll try to step through. So let's assume that the incoming observations that came in via email, they go in here. We take observations from anyone, provided you have an observatory code and you can meet our sort of quality standards. We will accept observations from anyone. We think you've discovered a new near-Earth asteroid. It's a little bit of a tighter category. We would call trusted sources. Those observations go rapidly into a pipeline that handles just potential near-Earth objects. We check the format of your observations. We check to see if there are duplicated observations. We check to see if you've sent in things that have already been published. I mention these things because each of these checks, every day hundreds of observations are submitted to the MPC that fail these 2 checks. We get a lot of repeat submissions and mistakes like that. And it is a great challenge to get through that as fast as we can to get to the stuff that we need. We check submissions for great circle departure. That means we pass a great circle through the two observations, and if there's large deviations from that motion, great circle motion, we think maybe you have an artificial object or you may have badly measured positions. Then we go through a set of checks for known objects. That's what all of these things do. At any point, anything that comes out of those checks goes into our supercomputer for routine orbit computation. And I call that a beast because it's literally a supercomputer with hundreds of cores, so that we're able to process literally millions to tens of millions of orbits per day. We have to be able to do that, and I'll explain later why. Now, I've got this little check down here that says Digest to new near-Earth object. Digest 2 is a program that computes the probability that any object might be a new near-Earth asteroid. And if it is, if we think it is, we send it over there to our near-Earth object processing pipeline. And we have dedicated computing power to that that cannot be used for anything other than checking for near-Earth objects. So now we've continued on, and here is where the near-Earth objects from the previous page have come in. Anything that is unidentified and scores higher than 50 on that digest will be posted on the near-Earth object confirmation page. This is a web page that is publicly available, and it also contains all the observations and orbits for anything there. So we put up our best guess for the orbit, but the observations are publicly available for anyone that would like to compute their own orbit, maybe compute their own uncertainty information, etc. I'm particularly proud of this. We have a very rapid transmission of things from our private pipeline where we're checking to see if the objects have been published or if it's a new object. And once it's a new object, bang, it goes to the confirmation page, and it's there for the whole world to see. Now, assuming that it passes through and we don't think it's a new near-Earth object, we have a place where we put these, which is called a single night observation file. And anything in there that we find to be a known object later or observations of a near-Earth object comes right out and is published. We send that back to the other pipeline. Now, interestingly enough, I run a program here written by MPC staffers that checks if there's a possible impact in the near future. And if that is the case, we go over here, and I've got a very special reporting and analysis engine in case we've got something we think might be on a short-term impact. I'll skip explaining about how we do orbits for all of the objects. If anybody wants to ask about this later, I can. It's quite a complicated process, and short arc orbits for near-Earth objects are extremely difficult to compute. So to be fair, in a lot of cases, we are guessing and using variant orbit techniques that are, and everybody's got things they do. Andrea Milani, Steve Chesley, JPL. It's a tough problem, and we're all still learning about it. But let's say I've got something that might actually be possibly impacting the Earth in the near future. What do I do? We go over here, and now we're in the impact reporting and analysis engine. I'm curious if anything is going to come within 6 Earth radii in the next 6 weeks. If it's not, it's still on the confirmation page and everyone will observe it. However, if I have something that tells me that it may be within that range, I have an automatic reporting system that will contact NASA headquarters via email and text. And it contacts JPL Solar System Dynamics Division by email and text. This includes Lindley Johnson, Don Yeomans, Steve Chesley, Paul Chodas, Alan Chamberlain. These people are alerted immediately. And I can tell you I'm on that list. And when this happens, I get woken up in the middle of the night. That happens about once a month where we've got something that merits at least attention to get me out of bed to give it a look. Now, once that has happened, usually Gareth Williams, the Associate Director of the Minor Planet Center, is up and cranking away on the object as well. We run some variant orbits, and we compute the fraction of those orbits that impact. So this is an uncertainty calculation that does the best guess at determining what we think the impact fraction or impact probability is for the object. If we think the impact is certain, nobody panic, don't panic. But what I do is I will call Lindley Johnson at NASA headquarters and make sure he knows what's going on. And to be clear, I have called him with an impact imminent. Get to that in a little bit. If I've got one that falls solidly in the middle, I will probably call Steve Chesley and get to work with him. The reason being that the Minor Planet Center has extremely good software for detecting the likeliest of impacts or the least likely. In the middle, it's really, really good to get someone who uses a completely different treatment for the orbital elements and uncertainties than we do, and Steve Chesley or Andrea Milani at the University of Pisa. They are people that are really good at that calculation, so we'll alert them. If there's a small chance or no chance of an impact in the near future, I will turn around and announce this object to the community when there is sufficient information to make that call. I want to keep in mind here, and I want you to keep in mind, that while all of this is going on, these observations are public. Observations in orbits are publicly available. And so, you know, it's a great system, and I have to say I'm really proud of how this has worked in the past. So, to give you some notes on impacting objects, we've already detected objects on an incoming trajectory on their final approach. And the first of these was an object called 2008 TC3, discovered by my good buddy Richard Kowalski of the Catalina Sky Survey. He was using the 1.5 meter telescope on the top of Mount Lemmon for the discovery, and I've included an image here. This little purple circle is showing you what the object looks like, and you know, I wish they had a little flag posted on them that said, "I'm going to impact the Earth." They don't. All we have is the positions, and that's how we've got to do the work. Got a shot over here of the trajectory of the object on its final approach. This is done by JPL. And you can actually see that the orbit curves a little bit because the gravity of the Earth focuses the object, you know, and sort of draws it in just a little bit at the end. It's very fascinating physics associated with that. And this image here, provided by someone at the University of Khartoum, shows something a lot of us are probably familiar with, which is the train that you see when we launch a spacecraft. If you've ever watched the shuttle go up or a spacecraft go up, you see this funny curved luminescent train in the sky. That's where the differing winds in the upper atmosphere have spread out the exhaust plume. Well, however, look at this. This is from something that was coming down. Once the object ruptured in the lower atmosphere, the train discontinued. And so this is really wild. If you show this to anybody that's worked in the rocket field and you don't tell them what it is, they'll say it's a rocket launch, and then you tell them it's a meteor, and they understand completely. I would like to note also that we recovered pieces of this object from the ground. So it's the first case of observing an object in space, predicting the location. You know, I had so much fun with this when we knew it wasn't going to be a damaging impact. Gareth Williams and Steve Chesley were trying to refine the prediction as where it would land on the ground, and I believe they were within a few kilometers in the end as to where it actually landed, which is really tremendous. And we did this with a you know, fairly short baseline of observations. We have another object that impacted, and this is a very instructive case for people that are paying attention to the field. This is 2014 AA. It was discovered prior to impact, but literally everyone in the field was out on holiday. It was New Year's Eve. The entire MPC staff was out at New Year's Eve celebrations in separate places. I didn't know about this until just before the impact. And what I've put up here is an image of the trajectory plotted by Steve Chesley and the really cool infrasound measurements of, so when something enters the atmosphere and explodes, we have these infrasound detectors that are in place to see, you know, to make sure we know if there's a nuclear explosion that has gone off in the world somewhere. They're really good at detecting asteroid impacts. And so we combined Steve's prediction with the infrasound measurements and confirmed that this object landed in the ocean. But also note that my buddy Richard Kowalski seems to be really good at finding impacts because he found this one too. I don't know, maybe he's got the knack for it. Okay, so now I'm going to shift and talk about the data flow of the Minor Planet Center. We are required to keep up on things in real time. There's really no sense in warning of impacts a day late, right? So, 2014 AA aside, we try to keep track of things as much as we can with a 24/7, 365 operation. That can be difficult. Also of note is that greater than 99% of the incoming observations we get routine main belt asteroids, or MBAs. So the near-Earth object is really a needle in a haystack. Near-Earth objects can and do hide with main belt asteroid-like motion. There's really no option. We have to publish and process everything as fast as we can. We average a few million publishable observations a month. This means observations that I could confirm matched known objects or were new objects with sufficient information to announce. On a really good night, we can receive 200,000 observations here. So this is an extremely busy place. There's 750,000 orbits on file, and that number is growing all the time. We have to handle it in real time. You can imagine how complicated that might be. The bulk of the data that we get come from the Catalina Sky Survey, they come from Pan-STARRS, come from Spacewatch, they come from a few other programs, and the rest of that tends to be rather small numbers of observations. It doesn't mean they're not important, but the bulk of the observations come from a few large programs funded by NASA. And I believe some of the other presenters have talked about those things. So here's an image of the sky coverage for a sort of 1 month time frame this year. And really this shows you, look at the coverage. There are just fields all over the sky. The bulk of this is done by the NASA-funded surveys, although this down here is really cool. This is from an amateur program in the Southern Hemisphere. They're run in Brazil. I believe it's the SONIER program. They found a few comets, a few near-Earth asteroids. Their contribution is to cover the southern areas of the sky because the Northern Hemisphere surveys cannot cover that area. Very cool. Each of these little boxes that you'll see with a particular color was a field that was shot on one night and scanned for near-Earth asteroids. As you can see, there's a tremendous amount of work that gets done here, and I am unbelievably impressed given where this field was 20 years ago when I started observing. It's really, really fantastic. So I'll talk a little bit about how the Minor Planet Center communicates. We've got various forms of communication, and it's important that we do a good job with it. The first thing is we have a web page like everyone else. It's got some informational things. You've got a tab for observers, which contains links to many of our tools, the confirmation page, our ephemeris programs, etc. Got a little bit of stuff for the public. We do blogs, things like that. Notice we have a Twitter feed over here. We announce, for example, all of the objects coming within 30 lunar distance of the Earth on our Twitter feed, so you can get a piece of that. And we also chatter on there a little bit. It's good to keep in touch with people. Got a link to the International Asteroid Warning Network page, which I'll talk about later. We issue minor planet circulars, electronic circulars, give you announcements of what's going on, publishable observations, etc. So really, it's a varied way of communicating. We receive observations generally through email, but now we're switching over to curl, which is a feature that allows rapid communication and checking without going through emails. The reason I've done that is that I get, as you can imagine, a lot of personal emails, and I don't want the observations confusing my personal email file because I really have a lot of people I have to talk to. We communicate outgoing designations via email, and we are working on a very sophisticated relational database for which the community can use for lots of queries, and I'm really hoping that once the relational database is up and running, I'll get fewer personal emails about the MPC data. All right, so now I've talked about what the Minor Planet Center does. I'm going to shift and talk about what the International Asteroid Warning Network is and what it does. I believe it was important to get all the way to this point, give people a good handle on what the MPC does. So the International Asteroid Warning Network was suggested by the General Assembly of the United Nations a while back. Now, this was taken up by the Committee on the Peaceful Uses of Outer Space, who established a working group on near-Earth objects. Part of that was an action team. And I present you this information because, and I may not have it all right? It's been fairly complicated, and there's been a lot of misinformation in the press about how things went. The International Asteroid Warning Network is just being formed. There are a lot of pieces of it that already existed, and part of Action Team 14's job was to go through and assemble the things that we had so they could report to higher up than that. They suggested that we could start building this International Asteroid Warning Network by linking the already existing near-Earth object programs such as the Minor Planet Center, active survey teams, European Space Agency, University of Pisa, JPL, etc. There are a lot of pieces of the near-Earth object game that have been in place, and getting them assembled in this fashion and recognized by the United Nations is a really important step, and it was, an honor to be part of this. The next slide here is a little complicated with a lot of words. I'll cover some of it. This is from a presentation that I gave in Vienna at a United Nations meeting, and again, it was way down on the list. It was to part of the Science and Technical Subcommittee of the Committee on the Peaceful Uses of Outer Space. So we were there, Lindley Johnson, Don Yeomans, and I were presenting, and rather ironically, we were there because of 2012 DA14. It was a good time to talk about the monitoring that was being done, and of course, Kelly events got impacted the day that Don Yeomans was presenting the United Nations. So it was rather timely and ironic. So the functions of an International Asteroid Warning Network are to discover, monitor, and physically characterize potentially hazardous objects. Other functions would be to provide and maintain a clearinghouse for the receipt, acknowledgement, and processing of data. That would be the Minor Planet Center. There will be a global portal serving as an international focal point for communication, accurate and validated information on the population, and to coordinate campaigns for interesting objects. The check marks that you see over here indicate these are things that are largely in place. The empty boxes below are things that are not completed yet. There is a lot of work to do to establish this network in the best way possible. We need to recommend policies and criteria regarding thresholds for notification of an impact threat. Obviously, communication is critically important. We need to develop a database of possible impact consequences. That is a very complicated job, obviously. We need a way to assess the hazard analysis results and communicate them to entities that should be identified. Again, imagine how difficult some of this stuff is. And there would be a way to assist governments in the analysis of impact consequences and the planning of mitigation responses. Now, I've put together some of the things that the International Asteroid Warning Network needs right now, and obviously this list could grow quite a bit. I want to say right up front, I have not put it in this particular slide in as much detail as I would like. The communication down here is critically important, and I think everybody that's watching this presentation knows that the ability to communicate facts calmly about potential impacts is critically important to the entire process, and we need a lot of work on this. And we've been working with people whose job is to communicate other hazards to the public and to governments, and we're just starting there, and I just wanted to call those people out right now that we are working with them, and there's a lot to do and a lot for us scientists to learn. So now we'll go up here to my dedicated ground-based telescopes capable of surveying the sky down to 20-second magnitude. We need this sort of thing to improve the ability to predict impacts and defend the planet. Right now, the sky is not being covered down that faint. And if you go back to the studies in the past, the Science Definition Team report, or the NRC report, we need to go fainter than we're going now to do a better job. We need a dedicated ground-based system for astrometric and physical observation follow-up. We need to be able to characterize the objects. We need to know where they are. I believe the next step in adding a factor of 10 on the discovery rate is a space-based infrared survey. Now, that's expensive. We know that there's NeoCam being talked about. We know Sentinel is being talked about. This is the next big piece in my mind. And really, hats off to Pan-STARRS and Catalina, principal investigators Richard Wainscoat and Eric Christensen. They have begun the process of survey cooperation and collaboration. We have limited resources, and so using those resources effectively and sharing the sky is very important. I would also point out we've got the the Space Watch program, which coordinates its follow-up observations. They're very careful to use their follow-up facility as efficiently as possible. And when you do this and you share the objects that need observing or the areas that need observing, we have a really bonded setup and everybody contributes in the best way that they can. So this chart shows the existing worldwide observing network. This is from a slide I showed at the United Nations talk I gave. It looks pretty impressive. There are lots of telescopes all over the world. Look at the density in Europe, Japan. Japan is famous for observations of comets and asteroids. We've got telescopes in Australia and Southern Hemisphere, and look, yay, here's pan-stars. However, while 46 countries submitted data to the MPC last year, 46 countries is pretty cool, right? 95% of the data came from just a handful of observing teams. And so, yes, I am grateful for what we have, and I can also wish that I had more and fainter observations arriving here. Now, I was positive before. I want to talk about areas of little need as we're going forward. We don't really need more ground-based telescopes that can only observe to around the magnitude 20 for survey purposes. As you could see, the sky is covered rather largely by the main survey programs. And again, hat tip to my friends in Brazil who looked at that chart and said, hey, we can contribute. We'll go to 19th or 20th magnitude, but we'll stay out of the way of the surveys, and they find stuff. That's the kind of contribution we need. We don't need repeated coverage of the sky to 19th magnitude in the northern hemisphere. We also don't need poor quality follow-up of observations to be of 19 or 20, and the simple reason is that that's already being done by the survey teams. You know, pan-stars covers huge amounts of sky every night. They go to 22nd magnitude or 21.5. They're going to find a lot of the objects incidentally that other groups are targeting. And of course, this is the reason much of this work is being done by the surveys. I want to call out the amateur contribution. This is one opportunity I have to do it, and I want to make sure the record is straight on this. When I say amateur astronomer, I mean an unfunded expert astronomer, right? These are people who are using their own time and money to contribute to this field. And I know people that have done this contribution with their own money, their own telescopes, their own time, for just about as long as I've been alive. Certainly longer than I've been working in the field. And I want to tip my hat to them right now. While they don't discover that many near-Earth objects anymore, in fact, it's under 2% annually, they make valuable contributions to the field. We get follow-up observations for objects on the near-Earth objects confirmation page. These are critically important. They allow me to improve the orbit, check impact predictions. They allow my friends that run radar facilities to actually locate objects. So, you know, they send a message out. The amateur astronomers go, as do other professionals, but a lot of times the amateurs are on it first. Observe the objects so that the radar knows exactly where to point. There's a huge group of amateur astronomers doing light curves. This is for shape models and spin orientation. Think about how important that is. If you're going to send an astronaut to an asteroid, you want to know how fast it's spinning and which way it's spinning. Amateurs are helping with this. There's photometry for phase functions, rough composition, surface composition, all sorts of things. There's even a guy that computes orbits for things. I interact with a guy that, Bill Gray, who does orbit calculations for everything that's on the confirmation page. Bill and I talk almost every week, and he's very good at doing impact predictions, which is really kind of cool. Other thing is here, I'll put an exclamation here, communication. There's an army of amateur astronomers out there that are communicating in a positive way about the work that's being done in this field. I cannot thank them enough for that. So now I'm going to talk a little bit about the future of NEO surveying. Right now, there's a lot of chatter about what's going on, and these are the things I think are going to make the biggest impact in the short term. The Catalina Sky Survey is upgrading to very large CCDs and also focal reducer and a large CCD for their system. They're the world leader in terms of near-Earth object discoveries right now. All that's going to do is make them discover more faster. We've got Pan-STARRS telescope, one telescope operating full-time for near-Earth objects. So again, it's changing the data flow here pretty dramatically. We always have to be awake on that. There's a program called ATLAS, and there's also the LSST, Large-Scale Synoptic Telescope. ATLAS will be an all-sky survey to the magnitude 19 to 20. We're not sure how faint they'll go. They should cover the whole sky in every couple of nights. So They will help with the short-term impactors. The LSST, it's quite far in the future. It's in the mid-2020s as far as I can tell. It would be an all-sky coverage every 4 nights to VO24. However, I know that these two things are going first, and quite often, I don't want to focus too much on things like LSST that is, literally a decade out right now. Something else might pop up between now and then. There's a lot of talk about a space-based infrared system, Amy Mainzer's NeoCam or the B6 Sol Sentinel project. These would be spectacular, and even they have a shot of operating, I think, before LSST. Somebody could correct me if I'm wrong on that. Those would make a huge difference, the space-based systems, in terms of discovery. So I'll summarize here. The Minor Planet Center is the nerve center of worldwide asteroid observations, and it's a key operational node of the International Asteroid Warning Network. Near-Earth object discovery and tracking has reached wide importance. The United Nations is talking about this. You've got to figure it hit the big time. And I think that is great. I'd like to think that the world as a whole is looking at this problem. This is a problem that actually, if there's a disaster, you might actually be able to stop it. We can't stop tornadoes or hurricanes or earthquakes yet. The idea that we could stop an impact, I think, is kind of romantic. It's the first time that we could do something like that. This field is dynamic. We've got many projects are improving their detection ability, and we'll discover more and smaller objects in the near future. There's going to be other projects that come online. This will absolutely be an exciting and dynamic field. It is right now, and it will just get more interesting and dynamic. All right, so with that, I will stop and take questions. Thanks very much, everyone.
Thank you, Tim. I would like to start out with some questions that deal a little more with the operation of the MPC. How long does it take for you to process the observations from, say, the Catalina Observatory? Are they completed the next day after the night of observation?
Yes. So we currently have excess computer capacity. When the near-Earth objects arrive here, the Catalina Sky Survey tends to send them in real time as they make the discoveries. It's one of the great strengths of the Catalina program. They have observers on the telescope sending things in. The bulk of those observations are processed within 5 minutes because I want them on the confirmation page as fast as possible. Their non-near-Earth asteroid submissions are usually completed. They'll send them in, when they close the dome, and we've usually got it done within the hour.
Cool. Now, let me pursue that further. Suppose you do get some interesting objects from Catalina, and you go ahead and work them out, and then 3 hours later, you get pan-stars, which may have more observations of the same object. Do you connect those then, or do you publish them as separate objects on the confirmation page?
Yep, they're connected automatically by the software. We've got really, I'm very impressed with my people and their ability to put together software that does that linking process extremely rapidly. We do a good job with it.
If the object is of interest, like a potential future impactor, do you call on other professional astronomers to make more observations, or do you really depend on both the rediscovery from the survey and the amateurs?
So if I've got something that I think has an impact probability, 50% in the near future, in a few days, I will huge. Yeah, I'll email people directly for that. But the system works so well that once something goes on the confirmation page and it's a high priority target, it will be observed by either a professional follow-up team or an amateur follow-up team within a day. Just the way things go these days. It's amazing.
How does the data flow go for NEOWISE or any other space-based system that's obviously has its own central outfit that's processing data? Do they still come to you in a timely way like NEOWISE?
Yeah, NEOWISE tends to send things 2 to 3 times a week. And, they have a fairly sophisticated image processing pipeline they're operating. And they ship the data down, process it, and then send it to us. And we turn that around very rapidly. I have to say, processing space-based data was a challenge when we got started, but we licked that problem, and it's fascinating physics associated with it. That's all I'll say.
Question here is whether the NEO confirmation page is getting adequate follow-up. And then I might put that another way and saying, how many objects do you lose?
I'm going to answer this honestly because that is my nature. I think we lose too many objects. And right now we have quite a lot of survey capacity. And for pan-stars, let's say, they find 15, 20, 30 objects. These are all going to be V magnitude 21 to 22 in general. There is not very much follow-up at that level. Bob McMillan at Spacewatch, his team can do those objects. But Bob can't do 100 of them a night. And we are taxing the follow-up teams right now.
Are professional survey groups like Catalina, do they have dedicated follow-up telescopes, or do they just do the surveys and follow-up if it happens to be in the field?
Catalina doesn't yet have their own follow-up system, but it's very close. However, they target their own objects with the 1.5 meter, just as a matter of course. They don't want to lose anything, and the Catalina team loses the least number of objects. So they discover something with one telescope, they follow it up with the other within hours, and then it's easy to locate it the next night.
You emphasize the need in the future to go to fainter objects, be fainter than 22, for instance. And you talked about LSST and the space-based, but if someone wanted to use an existing telescope and go deeper, what does it take? Is it aperture? Is it a better detector? What can they do?
It's almost strictly aperture. You need a big telescope. And we just have been getting some observations from the dark energy camera operated at Cerro Tololo, I believe. And, that's on a 4-meter telescope. And they're going really faint. And once you go that faint, you pretty much have to do your own follow-up. So you've got to build the follow-up into your program.
How do you deal with the issue of objects coming from more or less the direction of the sun? Obviously, no one observes them, right? Not if they're in the daytime sky.
About it. And I can tell you, when Chelyabinsk happened, I was relieved it had not come from the other side and come through opposition and was missed. Things that come from the sunward side, you literally get seconds of warning, like we had.
Now, Chelyabinsk was only about 20 meters in diameter. If it had been coming from the night sky, what do you think would have been the scenario and whether it was discovered or how well it was followed?
Well, given that we found 2008 TC3, which was about 1/5 the size, I'd have to think we would have had a very good chance of finding the Chelyabinsk impactor if the trajectory was reversed. And I expect we would have predicted the impact within 2 sets of observations over a half hour or an hour. We would have known what was happening.
Cool. Can you talk more about the TC3 impact over Sudan? How was it announced? Was there a special alert? How did you do that? There was remarkable follow-up over just a period of a day of getting observations. Can you work us through that scenario?
Yeah, so I'll try to keep it brief. I can see lots of questions popping up here, so I'll try to be brief on this one. I got up at 6:30, made my coffee. The computer alerted me to something that it had never seen before. I processed the observations, and it told me the thing was going to impact 12 hours later. It was certain. And so I called Lindley Johnson, and in the meantime, Bill Gray had already noted and posted on the Minor Planet mailing list that an impact was coming. And so while we were working on our announcement, people knew that it was going to impact. And so a bunch of observations were made all over the world, starting when that had happened. And of course, we issued an announcement. You could imagine it took a little time for NASA to okay an announcement of the first impact, right? Yeah. So Lindley was quite busy scurrying around probably the Capitol. I don't know what he actually had to do that day, but a few hours later we got the announcement out, and there were hundreds of observations made prior to impact.
So you're suggesting there actually was some significant delay imposed by getting the okay from NASA headquarters?
Only to issue the actual formal announcement, which we have a procedure in place. There was no procedure in place at the time. Nobody knew, when I was stunned. If you'd asked me the day before, would I ever see an impact predicted, I would have said, of course not. It's too remote. So we were all quite surprised.
And do you think you are missing other objects of that size that come in the night sky? In other words, are your observations consistent with what Peter Brown suggests, for instance, from the infrasound network for high altitude explosions?
I have not done the bias calculation. I'll be very honest. I will give you my gut. My gut feeling tells me that I have observations of objects that were lost that have impacted the Earth. That's
right. I mean, there have to be some, sure. On the future telescopes in space in particular, I presume these are all like Sentinel, they are NeoCam, they are survey systems. Are there any expectations of using space telescopes for follow-up or for doing any critical observations that are timely and are not just part of a long-term survey?
I don't really know about that. I suspect, Hubble, JWST, these sorts of things could do that. Spitzer, right, they're doing some of these things right now, so I would assume that would continue.
Is it possible to use the SOFIA airborne telescope in a constructive way as part of this program? I say that because it's very expensive to operate.
Yeah, I expect that you can provide some good information, infrared physical type observations, yes.
I'm going to ask you to go back to your flow chart and explain a little more about how an actual orbit is calculated, not the mathematics, but how many observations do you need of what quality in order to get a halfway reliable orbit?
Okay, that's an excellent question and one I love to answer. For a near-Earth object that is moving rapidly, we have a set of programs that fit the first and last observations to a suite of orbits based on a guess for the geocentric distance and varying all the velocities between a parabolic orbit that's just barely bound to the system down to a circular orbit. When we run that piece of software, it tells us which orbits are likely. I can check the residuals, find the one with the lowest residuals. That check is done extremely fast.
Excuse me, what do you mean by residuals?
Residuals are the difference in the other observations from the orbits I've calculated. So if you imagine I have positions like this, and then positions in the middle here, I compute various orbits based on just the knowledge of two positions, and my best orbit is the one that fits those others the best. We minimize the residuals that way. I know this is a little complicated, but it's what we do. Now, once another observation set comes in from a different telescope or even the same telescope, I can quite often use Gauss's method, which, I love it, right? This over here, Gauss's method. Yeah, we've had some advances, but I'm still using something that was written 200 years ago. And it works. And it works really well for near-Earth asteroids on 1 hour to 2 hour timescales. And so that's the process. If I have 6 or 8 or 10 observations over several hours, I can often compute a pretty good orbit for that object.
You talk about this now first person. How much of this is automated and how much requires Tim Spahr or someone in your office to sit down and do the work?
Boy, do I love to be able to answer this. I apologize. When I say I mean we, the Minor Planet Center, computers.
Okay.
No, I am not tinkering with orbits that often. We have an amazingly I'm proud of the automated system created by my people here. The staff, James Davies, Sonia Keys, Jose Galache, Mike Rudenko, Gareth Williams, they've all written things that we use. The digest program is maintained by Sonia. Gareth has written an awful lot of the routines that go through and compute the orbits, but the key to all of it is that almost all of it is done absolutely transparently by the computer. And it knows, looks at the observation distribution and says, hey, I ought to try this routine. And if the distribution is larger and longer, it'll try another one. And the confirmation page operates automatically about 96% of the time without any manual intervention whatsoever.
So this includes the actual posting of the discovery or the observations. That's done automatically also without someone looking at it?
In the middle of the night, it's got to go by itself. I can't be up all the time.
Back on that chart, I have the question as, what does the greater than 50 and less than 50 mean?
Okay, let me put it over here, these two things right here. So this is a program that estimates that the object is consistent with the motion of a near-Earth object. If it thinks that that is a sort of 50% likelihood that the object is a near-Earth object, we stick it on the confirmation page immediately. If it's not, the observations are kept here, and the observer can go observe it again. But really, we want to err on the side of most things being, something we're interested in. And right now, the funny part is that the process says, okay, we think 50% of these things will be near-Earth objects, but currently I think it's running at about 40%. So we're not sure why the difference, but we don't really care. Most of what we post on the confirmation page is interesting, and around half of it turns out to be new near-Earth object.
This chart has a black hole in it somewhere. One of the arrows goes to your single night stand or single night file and then stops. Does that mean that those observations are discarded?
No, sir. Those are kept in the system and checked and rechecked every single day to see if I can remove something from that and stick it in the main pipeline. The other thing is that those observations are not formally published, but they're on our website so that any other researcher can download them and check our work.
So a decade ago, that was a question, right, that they might not be accessible, but you've got that figured out for anyone who really wants to go into this nitty-gritty of single observations.
Yep, and it's always been my philosophy that if people want the fire hose, you should turn it on.
I have a question about the quality of observations. These are often faint objects. They're observed near the limit of the telescope system. Is there some signal to noise criterion or something that you apply to decide whether the observations are real, or is that up to the observers?
Currently, this is up to the observer. I prefer that the observations that are sent to the near-Earth object pipeline be highly reliable. Obviously, we don't want to be chasing ghosts there. I also check on, let me see if I can go back here. Right here, this great circle motion check. This will check how likely the motion is with a real solar system object. And quite often I get things in there where somebody will send me 4 observations and the object reverses direction. It goes from north to south to north in 20 minutes. That's unlikely. In fact, it's impossible. And so that check does return a lot of observations to the sender and say, I don't really think this is real.
So I suppose there's an iteration. I think I remember a few years ago there was an object that was important, and I think the University of Hawaii observers had a slight clock error. And that's the sort of thing that you're likely to find and then send back to them?
No, clock error is very difficult to find. And we have created a very sophisticated pipeline to trap errors, but clock error is one that is just a tough one. And so that took, I believe it was David Tholen, who is probably the world's best astrometrist, who figured out what was going on there.
we're coming to the end of questions here. Let me ask you if there's anything you would like to expand upon, or if not, I'd like to know a little more about the prospects for the international group. I have seen a number of the IAWN. I've seen a number of international organizations put together where people are interested, but as you note, they aren't actually finding or checking up on any asteroids.
You know, I'm going to try to be as diplomatic as possible on this one. I'm positive on it. I have met with the people. We had a steering committee meeting, an IAWN steering committee meeting here in January, and I felt genuine interest, and I think people want to contribute. The UN was very clear it's not paying anybody to do anything, but the European Space Agency, for example, is spending a good bit of money on near-Earth objects right now, and I expect this to continue. And I think the Russians, it was pretty scary for the Russians what happened, and I think they want to spend some money on it and look into it. And when the Russians decide they're going to do something, they will do it.
Well, I guess part of the reason that I wonder is that the current survey programs and the MPC and the JPL group have done such a good job. You've really harvested all the low-hanging fruit. It must be very hard for a new observational group to come in and really be able to contribute much compared to these people with 20 years of experience.
It is, but I would point everyone to what the dark energy camera has done in the last 2 weeks. The secret is simply to go fainter. And look at that. That's, you know, Trilling and Allen and other people. They're on the minor planet circulars, electronic circulars. They found dozens of near-Earth asteroids by just going fainter. So it is possible.
You haven't said much about the physical observations, things like light curves to get spin periods and amplitudes that I would think amateurs could contribute to. And I don't know if they even go to the MPC. What's the scene on that?
Excellent question. We archive the light curves here. The real champions of the amateur involvement there would be Brian Warner and Alan Harris. And they have really, really facilitated a wonderful collaboration with the amateur community there. And, you know, Brian dances the line between amateur and professional. You know, he started from the amateur ranks, and I believe he's been funded to do this.
And work. Alan Harris is the same Al Harris that spoke in this lecture series a few weeks ago, yes?
That is correct.
Okay.
So the only reason I didn't mention anything about this is that, you know, to stay within 40 minutes, I had enough stuff just to talk about the dynamics end of it. I took one whole slide to tell how proud of those people I am and the contributions I'm getting from the amateur community, specifically in the light curves.
You might want to conclude by talking about the impact on MPC if something like the Sentinel telescope goes up and supposedly will increase the data discovery rate by a factor of 40.
I would need a couple more bodies and some more computers. That would be the answer. I would need to spend some more money, but we can do it. We have scaled up. If you think about it, when I started at the MPC, we had not even numbered asteroid 10,000, and we're up to 400,000 now. The people I've got here know how to make scalable software and scalable computer systems, and we will do it if needed.
Do you want to say a word on that about how it goes from numbers, which you supply, to names, which people like?
The naming process, fortunately, is not handled in any way by me. Gareth Williams serves in an unbelievable capacity on the committee that helps with the naming. But what happens is the discoverer gets to propose a name, and it goes to a committee of people to evaluate if they think the name is acceptable. And I am outside of the loop on that completely.
International Astronomical Union Committee?
Yes.
And the IAU also sponsors you. Traditionally, way before NASA, the IAU was sponsoring the Minor Planet Center, right?
Yes.
So there's an international connection from the beginning.
Yeah,
well, thank you, Tim.
There's a great history of this organization. Yeah. We should have a whole talk on that. I could have Gareth do it, and everybody would love it. It's fascinating.
Yeah. Well, thank you very much, Tim. This has been a fascinating discussion, and I want to congratulate you on the unique work that the MPC does that makes so much of this enterprise of near-Earth asteroids and planetary defense possible.
Thank you very much, and it really is an honor to be here and work with the people that I work with every day. This is an exciting job, an exciting place, and it's a good place to be.
Thanks.